Hi, I'm Rohan, and I work on computer vision here at the Advanced Technology Group. I'm going to talk about the unified visual understanding at Pinterest. Most visual applications at Pinterest are powered by the technology known as the unified visual embedding. This powers three core visual products at Pinterest. The first is Flashlight, where you can find visually similar pins to a given pin or a part of it. Lens, where you do the same but with photos taken from your camera. And Stella, or Shop the Look, where we match parts of an image to an exact product pin. You might have seen a few of these during a few different talks today. At the heart of all three of these is an embedding based retrieval system. But what is an embedding? Specifically, a visual embedding. So, given a raw pixel based information from images, we want to boil them down to a lower dimensional vector representation such that semantically similar images are near each other in this low dimensional space. For example, you want the embedding distance between the shoe and the table to be higher than those of the two tables. The distance measure can be any common metric like the Euclidean distance or cosine similarity or something like that. This is how you would build a visual search based product by fetching the nearest neighbors based on the distance given for any given query image on a given corpus of images. One thing to note here is with our three different visual products is that the domain of images are very different. The very first versions of these products had to use three different embeddings because of the domain shift problem. As flashlight embeddings would not work well on lens embeddings would not work well on Stella, and so on. So after lots of careful modeling work and calculating the losses for all these tasks together and backpropagating them through a single network, our team launched the first unified visual embeddings for all three tasks in 2019. Unifying them meant that we have the same model backbone for all three of our retrieval-based tasks. And the idea is that a single model benefits a lot from the combined knowledge of different domains by training the same model in a multitask learning setup. When we deployed this unified model to production, we saw improvement in the retrieval performance for all three of these products. In the next version of the unified visual embeddings, we really ramped up our multitask learning setup by adding several other vision-specific tasks, such as a fine-grained attribute classification task, an image styles classification task, and expansion of Stella to the fashion domain. Previously, it was restricted just to home decor. Now that we had established that this works great for visual applications at Pinterest, we also realized that these foundational models can be much more powerful than that. Pinterest is a growing platform with many different kinds of images and newer applications being thought of every day. So let's say you're part of a product development team and want to train and deploy a new vision-based model. There are several obstacles that you need to overcome in order to make a new model production ready. You will have to make sure that your new model works well on scale, generalizes well for all kinds of images you'd see on Pinterest. You would have to set up infrastructure to be able to run these expensive computer vision models or run feature backfills, which can get pretty costly. Trying out new architectures, we look at archive or anything. There are new computer vision architectures coming up every day, and all of these new networks bring new challenges that need to be accounted for, mainly using new kinds of data and a lot more hyperparameter tuning. Here is where the benefit or the biggest benefit of using these visual embeddings comes into the play. We train these huge foundational models such that the representations learned here are rich and potent enough that it generalizes to any new visual task. So a product development team would only need to add a new task head with a few hidden layers or so, or any kind of a decoder, to build a new application, keeping the rest of the embeddings intact. Also, these embedding-based features can be directly used as part of visual representations for any new model. This is a playbook that has been utilized in many parts of the Pinterest tech stack, including in candidate generation, ranking, retrieval for our home feed, related pins, ads, inclusive filters, and many other surfaces. I think the last count is like 30 plus surfaces or so. So going back to our foundational modeling, from here we get to our third version launch. And because we only have to focus on this one foundational model, we're really able to like scale up the training and make sure that we incorporate all the best practices from state of the art methods and models. We first created our largest weekly supervised dataset with over 1 billion images, which is what we use to pre-train the model. By pre-training, I essentially mean that we want to prime the model so that it gets a general understanding of the kinds of images it can expect to see. Because of the scale of this pre-training, the representations that you get are even more richer and information dense than starting with randomly initialized weights. This was also the time where we switched from a fully convolutional model to a vision transformer-based model. The message from this third release was pretty clear to us. We need to train much bigger models. This is mainly due to the fact that convolutional-based models reach a diminishing returns point of model complexity and dataset sizes sooner due to the inductive biases that are inherent to them. Transformer-based models do not make such inductive assumptions and hence benefit much more from the additional computation in the form of layers and data. This is perhaps why in the text world we see models which have more than 1 trillion parameters, because most of the models are just pure transformer encoders and decoders. Vision hasn't gotten to that point yet, mainly due to the high bandwidth information channels and images, but the trend seems to be bigger data sets, bigger models. So we basically spent the last year and a half figuring out how do we increase the size of these models. We have a pretty big data set now with over 1 billion images. We just need big models that can utilize all of these data sets now. So we want to figure out how do we increase the size of these models, and more importantly, how do we actually train them? Because there are big limitations around GPU hardware, fitting models into GPU VRAM and stuff. One of the first levers we hope to utilize was the fully sharded data parallel, or the zero redundancy optimizer work that came out of Microsoft, I think, a few years ago. In order to understand zero, we need to take a quick look at how distributed data parallel works, which is the industry standard for doing multi-GPU training. The main entities that take up GPU RAM during training are the states of the model. The optimizer states, such as, so if you're using the Adam optimizer, it has several parameters per weight, each of them floating points, so they take up quite a bit of space. The gradients of the model during training, and the weights themselves. You would store a copy of these states in DDP, run an iteration of forward and backward loop on different copies of data, and then do an all reduce operation, which averages all these weights and copies them back to all the different GPUs during training. As you can imagine, you need to store the same model weights or the same amount of floating point bits of data on all GPUs, which can cause quite a lot of redundancy. In the zero redundancy optimizer, or zero or FSDP, instead of storing copies of all parameters on all machines, we chunk these parameters based on their layers and store them in different devices throughout the network. When we need weights or states for any given particular layer, we fetch them on demand. So for instance, if you have a huge network with like 100 layers or so, on any given instance, given the sequential nature of these models, you would only fetch the first few layers initially, get rid of those layers, and then fetch the weights for the layers after that. We can also overlap these communications and computations using a mechanism known as backwards prefetch, which lets you do these calculations and network fetches pretty fast. Along with FSDP or zero, another lever you can use is activation checkpointing. So in activation checkpointing, we reduce the amount of memory writes in order to save GPU VRAM. We essentially do this by discarding the intermediate activations from the model, but recompute them during the backwards pass. So for instance, on the image on the left, what you would see is during the forward pass, you have these intermediate states, S1 and S2, which are used during the backwards pass along with the output to calculate the gradients. Inactivation checkpointing essentially would get rid of those intermediate states during the forward pass, which makes the uh, VRAM slightly being able to accommodate more layers. But you calculate those uh, intermediate states again during the backwards pass. This makes the gradient descent step slower, but it allows us to fit larger and larger models. So with more GPUs, you can essentially fit bigger models, and you basically are trading off versus time with the size of the model. Finally, transformers can be very slow and memory hungry on long sequences. Since the time and memory complexity of self-attention is quadratic in nature, flash attention, an IO-aware exact attention algorithm that uses tiling to reduce the number of memory reads writes between the GPU high bandwidth memory and GPU on-chip memory. A simple description of what tiling or flash attention here does is in the computation for attention, instead of computing the whole queue dot product between the queue, the queries, and the keys, then taking a softmax of those, and then taking a dot product with the v vector, we do all of these together in smaller chunks or tiles computed on the SRAM and do the memory transfer between the high bandwidth memory and SRAM only once. All of these operations on smaller chunks of data or smaller tiles can be fused into a kernel. It speeds up operations even more. So going back to the models, given that we have a few tools in our toolkit that allows us to train big models, how do we actually make these models bigger? So despite the inductive biases, the weight sharing nature of convolutions make them an attractive option to increase the model complexity. In the original VIT paper, what you would see is once the image is divided into these patches, they are projected through this linear projection layer, which gives you a vector representation for each patch of the image. And those vector representations are then passed through the transformer encoder. So instead of using the linear projection, we initially add a small resnet there to get these patch features for our VID. Next, we tried to use the CourtNet architecture, which was an architecture which has repeated cycles of convolutional blocks followed by self-attention blocks. This helps increase the size of the model by a lot. So you can imagine there are a bunch of convolutional blocks at the beginning, then followed by many more transformer blocks in the whole transformer encoder part of the model. This helps increase the size of the model by a lot. However, our offline metrics did not improve as much as we scaled the size of the model even more and more. A reasoning to this was that perhaps the convolutions had too much of the biases that I was previously talking about to take advantage of the huge data set that we had. So in order to get rid of those biases, we essentially got rid of all the convolutional blocks, except for those in the patch featureizer. We found the patch featureizer, the convolutions in the patch featureizer to be still useful. And they weren't adding to the inductive biases because they were not part of the transformer mechanism. So instead of the VIT base variant that we were initially testing out with, we switch it out for a VIT large, use global pooling instead of the CLS token, which is usually used in the VITs. And this essentially gives us our first candidate model, which we call the hybrid VITL. The hybrid because we have these convolutionals in the patch featureizers, followed by a big VITL. And this model has around 500 million trainable parameters, and it improved our offline metrics for our multitask learning setup by a decent amount. Finally, we had a good blueprint of an architecture that worked well with the increased scale. Next, we just had to ramp it all up even more. So instead of our ResNet 9 patch featureizer, we scaled it up with a ResNet 50. So a 50-layer ResNet as the patch featureizer. And we added many more layers to our funnel VIT architecture. So instead of having the same sequence lengths throughout our transformer encoder, we add a small pooling layer in the subsequent blocks of transformers so that we keep reducing the size of the intermediate features a little bit during the training. We call this architecture the funnel VIT, as it kind of looks like a funnel. And we also increase the image dimensionality at which the model is being trained, initially from 224x to 256x images. Just this tiny change also adds a lot of complexity to the model, but also gives richer representations. During this, we also experimented with several different head training strategies. We altered the weight decays for several different layers and tested out different optimization strategies during training. We played with like many different optimizers. This finally gave us what we call the Penn hybrid funnel giant model, which is a model with over 1 billion parameters. With this giant model, we then optimized our training further by bringing down the training time with all the tools in our toolkit, like that I previously mentioned. What would have taken over 60 days took around 20 days for pre-training. And after that, we do 4 more days of end-to-end fine-tuning on over 20 of our visual tasks, including the retrieval tasks and the classification tasks and all the other tasks that I mentioned. Recently, for improving our metric learning specific tasks, we revamped some of our hard triplet datasets by hand labeling a large number of hard negatives, which also improved our retrieval performance by a lot. So we learned that improving the quality of the data helps quite a lot more than just architecture changes over time. This model was finally made compatible for inference using half-precision channels and channel last inference on the EC2 G5 instances, which has the NVIDIA A10 GPUs. We tested out this few different model distillation techniques to even further reduce the cost of inference, but it did not work out as expected for us. But regardless, we were able to launch this new embedding version. So this big model, which spits out these embeddings for these images, it works very well for all our different products with improved offline as well as online metrics for visual search, along with helping improve performance of the models that use these embeddings as features, such as in home feed or search. Finally, in terms of future improvements to this, we are excited by clip-style multimodal image text training, and we feel we can improve the visual representations a lot by incorporating textual information as well. We also feel that we can increase the scale of these datasets we train these models by the way of self-supervised learning. Recent works on masked autoencoders allow us to do this in like a scalable manner without needing too much human label data. And all the LLM work that is going on is pretty exciting, and we want to see how we can incorporate some of this in our training stack as well. With this, get to the end of this talk. I'd be happy to take any questions on this and hope you got a good understanding of how we unify our visual understanding systems here at Pinterest. Cool. I see some questions. Are the smaller heads typically classifiers? If and how do you use object detection in tandem with a foundation backbone? Typically, most of them are classifiers, although we have some regression tasks as well, which are part of this. The way you use object detection in this, we have been experimenting a few different architectures. You can imagine something like a SWIN PIT, if you've heard that SWIN transformers, those kinds of models. What they give you are these hierarchical representations during the transformer encoding process as well. And those hierarchical representations can be then fed into a decoder block, which takes representations from intermediate layers of the encoder. And you can basically have a decoder as a separate part of it. We've been playing around with certain segmentation models and detection models as part of this as well. So you can essentially use the intermediate weights from the encoders as a part of this. We are slightly over time, so I'll pass it off to the team. I'll be around to answer any questions or comments. But yeah, thank you so much.